if you still remember your stress strain curve, this is the stress, this is the strain, this is the stress, and you have an elastic region, and then up to your yield strength, you may actually go into yielding. Right, so this particular point, we call this the elastic region, or the constitutive equation is sigma is equals to the Young modulus times your strain, alright, which is the Hooke's law. Alright, that describes the behavior of the material at this region. Alright, and we say that there will be another equations, the strain equations, to describe your plasticity region. And therefore, let's do it now. We are somewhat in the part 2, because if you still remember, we have two important stuff regarding plasticity. So the first one was the criteria, the safe criteria. Alright, and then we briefly talk about the bending, the beam bending in process. Alright, now the second important stuff is our equation, because we want to know that what type of stress, maybe you have input a von Mises stress, what type of this stress will cause what type of strain, how much strain will be caused due to your certain stress that is gonna deal with it. Alright, so since we know that the strain, alright, the strain itself will increase after on when you deal with the plastic region. Alright, and therefore we'll start off with the origin as if you were to crop this out. Alright, let's say for example you were to crop this out. This particular is your U point, right, your U strength or whatever. If I were to crop this out, what I would have is something like this. Alright, instead of the stress, you write in terms of a von Mises stress, your maximum stress that you can hold until it starts to yield. Alright, and then this particular point is your yield stress, or we can just write as sy. Okay, or in your book is degree sigma y. So far so good. And then the curve may be something like this, it's a non-linear curve. Alright, for example, if you have a certain point, alright, certain stress, any arbitrary stress, you apply it, and then compared to this curve, you have a certain shape, certain strain, right? So this strain is what we call the strain equivalent proportion. It's proportional to your whatever thing that you are calculating. Alright, and this proportional, this EQ, alright, helps you to calculate your strain. Alright, this is the strain of your point, of your particular point. We call this thing is a plastic strain increment. How much strain have you increased? So you are actually interested of how much strain have you increased. So this is a very key understanding, although we can't see it over here, I don't know why. But still, at least you know that this is some increment from some strain increment. Alright, and then how do we derive this is that the small little strain increment, often when you input a certain stress, alright, is with regards to the devolteric stress, alright, where somewhat this things, if you minus away your hydrostatic, will be some values, maybe it's 3, 4, 5, 3, 4, 5, because it's symmetry. So this is your devolteric stress, or you can call this the KY, if you still remember the shear components of your stuff. Alright, and we know that the hydrostatic stress does not affect your plastic flow, and this is why we somewhat know that the incremental of the strain is proportional to your devolteric shear stresses. Alright, and therefore the proportional is indeed your proportional factor some d lambda. Right, we don't know what is it, but anyway, let's continue first. And due to some reasons, due to your flow rule, meaning how the material flow, alright, we come out saying that the d lambda, right, the proportional factor is actually 3/2 multiplied by your equivalent strain divided with your stress von Mises. Alright, so it's somewhat a form of a constants. Alright, so it's just some constant multiplied by your stress. Same as your if you talk about stress is equals to E over strain, if you have to rearrange, strain is equals to 1 over E stress. So this thing is somewhat very similar to this. Your increment of your strain is somewhat your like 1 over E times your stress, where your stress is your shear stresses or your shear components, and we call this the deviatoric one. So normally when you start to calculate, you need to calculate your deviatoric stress first, and then you find your increment, and then you find your Vollmesses, and you should get your incremental. And once you get your incremental strain, then you will know that, okay, with a certain stresses, I have a certain strain, increase of strain, and what is the so-called tolerance such that this strain can be acceptable or not, and things like that. An alternative method is also to use the safe or unsafe criterion, our U criterion, right, which is we have discussed earlier. And therefore, these are the two stuff that we talk about. Alright, the safety thing and your equation over here. Alright, so we have talked about the equation, and then in the previous parts talking about the U criterion is talking about the safety of whether will you yield after a certain boundary stuff. Alright, these are my piece and parcel understandings of the plasticity. Alright, as you can hear and listen, these are all very vaguely explained, and a thing or two are not very explicitly defined, but at least something there. Alright, so in the next lesson, alright, in the next lesson or the next video onwards, we'll do some examples, hopefully to know more things. Alright, I shall see you there.